naught, here is T naught plus T. So this is first order plus time delay to response. What the approximation approximates with, no delay, but in the response, essentially, that's what the Padé approximation. Okay? That's what it boils down. And with the Padé approximation, the characteristic equation becomes Renault. The smaller the d, the more trustworthy is the approximation. Remember, I showed you a Taylor series expansion at d equals 0. Okay? But unfortunately, it doesn't err the right way.
You said the smaller the d, the more trustworthy?
Yeah, the more trustworthy. Yes. And how do you judge d small or big? How can you say, I mean, after all, if I change the time from seconds to years, the number becomes a lot smaller. So how do I judge if the delay is small or big? Look at the ratio d over tau. Okay? Or d over tau dominant if we're talking about higher than first order system. So if that ratio d over tau dominant is really small, then the Padé approximation probably is going to be okay. Although again, it errs the wrong way, but probably only very close to the boundaries.
So if it's not very small, then you can't use it.
Yeah, I wouldn't trust it at all. If d over tau is 10, I wouldn't trust it at all.
Do you want it to be less than 1?
I can't give you any absolute value. So it can be, it is wrong no matter what. I can always find some KC that would make it wrong no matter what you give it. The other methods don't have that problem with the time delay. So why do we bother with Padé approximation if I can use the Bode or the Nyquist stability criteria that don't have any issue at all with time delay? There's a huge advantage when we're designing controllers that the Routh array has. Every other method needs numbers for Kc, tau I, and tau d. All other methods, direct calculation, Bode stability criteria, Nyquist stability criteria, can only be used by giving specific value for Kc, specific value for tau I, specific value for tau d. And in a three-dimensional space of parameters, that's a nightmare trying to figure out what designs will give you stability. In contrast, the Routh array can be done without giving any specific values for Kc, tau I, or tau d. We get inequalities. And in many cases, we can simply get, we're going to be closed loop stable as long as Kc is less than something, tau I is greater than something, which you cannot get with any other method. So what do I do for stability? How do I make an exam? Okay, often what I will do is I will use the Routh array, get results that I don't trust, and then I go to the other methods and verify with specific numbers that I pick from the Routh array if it is stable or not. And often a good example for me is to use the Routh array, find something that according to Routh array will be stable, and then do one of the more reliable tests that actually is unstable. But anyway, Routh array is the only test that will give us guidance for designing because I don't have to put specific values. So I have 10 minutes. Let me try to do a very simple example of controller tuning. Let's do an example of closed loop stability, where we want to design a controller to guarantee that I'm closed loop stable. And let's take even a case of something that is open loop unstable. So let's take, I have an open loop unstable system. And I want, if possible, to stabilize it with a PI control. So Let's see if we can finish it. I'll tell you what. Since I don't have much time, let me just do P control.
Ah.
But here's the system.
Phil was gonna say you can go.
Yeah. I
I
thought you
might
were
do
gonna.
another example on Wednesday.
I thought you were gonna let us go.
One, you haven't taken enough classes with me, but all my free is over. Let me go 10 minutes early.
If you think this has a happy ending, I'm not paying attention.
No happy ending.
Let's say I have so, here is my GC, just proportional controller. Here is my GU, and in this case, you can say, is GU open loop stable?
Open loops. No.
Has a pole of plus 1/3.
No.
Okay? I'll tell you what. Let me change something. I don't have to put full channel PI, but let me put the PI with fixed hour.
Yeah.
What's happening?
It's changing something.
Yeah, I stopped writing.
I just, it would be, I just want to make another point that I wouldn't be able to make. You know.
Change it again. Change it again.
All right, I'll change it again.
No, no, no. I'm just kidding. No.
Exactly what it is.
I was
You just
joking.
did. Back to the original. Okay. Okay, let's do it fast. Okay, so what's the characteristic equation?
Oh my god.
Has to be 5 minutes, I just realized that. So. Okay, 1 plus G UGC equals 0, right? That's always the characteristic equation. Right, Felix?
Yes.
So, 1 plus GU is what? 7/3s minus 1 e to the minus 0.02s times Kc must equal 0. Notice I haven't specified what Kc is. That's not polynomial. Okay? Not polynomial. But if I use Padé approximation, I approximate e to the minus 0.02s as 1 minus 0.02 divided by 2, d over 2. You can save that. This is the first order Padé approximation. So this 0.02. So 1 minus 0.02 over 2s divided by 1 plus 0.02 divided by 2. I hope my 2's and s's look different enough. I'm glad I'm not writing any 6. Not this here, okay, it's 2's. If anything looks like it. Okay? So that gives me
Ask
1
if
minus
he doesn't want to change it again.
0.01 times s
One more
over
time.
1 plus 0.01 times s. So the characteristic equation becomes that 1 plus 7 over 3s minus 1 times Kc, let's put the Kc up here, times 1 minus 0.01s over 1 plus 0.01s equals 0. Okay? 1 plus GU DC. 1 plus, this is the GU, this is the GC. The GU, I'm approximating this part by the approximation. You okay? Ring okay with me? I'm trying not to go too fast, that's why I decided to return to the simplest example. Alright, so you can make common denominator. Common denominator 3s minus 1, 0.01s plus 1. Numerator is the 1 becomes 3s minus 1, 0.01s plus 1, plus 7 kc times minus 0.01s plus 1 equals 8.
Is that 0.015 or 0.0s?
There are no 5s. This example has no 5s. There are
Oh
all
my.
S's.
That's an S?
Yeah, there are no 5s here.
That looks like an S.
Dude, I can not tell. Make him dollar signs.
Dollars.
That's what I do.
No 5s, all S's. On purpose, I picked an example that has no 5s. I was careful. So, numerator plus over denominator equals 0. That means numerator has to be equal to 0. So let me sum myself 3s minus
I'm
1
gonna be an engineer
times
anymore.
0.01s plus 1 plus 7 kc times minus 0.01s plus 1 equals. Which we can rewrite as a polynomial. So, s squared is 0.01 times 3, so 0.03 s squared. For s, I have minus 0.01 from here, plus 3 from here, and from here, minus 0.01 kc. Times that. All that multiplies s. Okay, from here I have 2s parts, minus 1 times 0.01.
Should be 0.07 kc.
Oh yeah, there's a 7, thank you. Thank you. I forgot the 7. And then zeros of the terms are minus 1 from here, and from here I have 7 kc. Equals 0. So that's the approximate characteristic equation. So let's make the root array.
God damn it.
How many rows?
Oh.
3 rows.
What time do we get out?
Quadratic, so it has 3
We get out
rows.
at 45.
Really tough one, guys.
We get out at 45.
Okay.
We're
So
done.
the polynomial I have, let's rewrite it up here.
43.
It's 0.03s squared.
You're gunning it.
And then for s, I have 3 minus 0.0 is 2.99 plus 2.99 minus 0.07 kc. And then I have plus 7 kc minus 1 equals. So, first row. Who will tell me first row? Well, I don't have time to ask you. So 0.03. Really perfect. Skip the next one. If you respond immediately, but nobody responded immediately. Right, that's the first row. Megan, okay. Second row. 0. 2.99. minus 0.07 kc. That's it. Last row. Remember the structure? Inverted staircase?
So 7 kc minus 1.
7 kc minus 1 is correct. Corner, corner. Right? Corner, corner. So, what is required for stability? No sign change, right? Stability requires no sign change in the first column. So, stability requires no sign change.
One more minute.
We know to have 0 positive roots. That's why we're stable. So, what must we have? Since this guy is positive, to have no sign change, the other 2 guys must be positive.
Yeah, but we don't know what KC is.
Yeah.
That's what we're designing. That's what we're figuring.
Okay.
That's the whole point of the example. To find for what values of Kc, if any, am I going to be stable. So, since this is positive, I must have 2.99 minus 0.07 Kc positive, and I must have 7 Kc minus 1 positive.
Oh.
So that gives me that I must have, from the first inequality, that Kc must be less, moving the side becomes less, than 2.99 over 0.07. And the second inequality gives us that Kc must be greater than 1. Putting it together, 1 over 7, sorry. Thank you. 1 over 7 must be greater than less than Kc and less than 299 over 7. So these values of Kc would make the closed loop system stable. Open loop unstable, these values of Kc would stabilize.
Right.
But the approximation means I don't trust the Routh array exactly. So I wouldn't trust a value very close to 1 over 7, and I wouldn't trust a value very close to 299 over 7. But somewhere in the midpoint, I would trust. Clear?
Clear.
Good. I try not to go over the speed limit.